Thank you. So my name is Andrew Moon. I'm a lead engineer at SP Energy Networks, and I work in the SP ManWeb region. And we've run historically some power electronic projects in Spain. One of them being Angle DC, which is a medium voltage strategic project, and the other one being LV Engine, which is a smart distribution transformer project at the LV level, which gives us some background and expertise in this technology. And we also have a project partner on board, UKPN, who have led soft open point projects as part of the network innovation competitions and LCNF over the past 10 years, so they have a good background too. So going into the slide, what we're going to present today, we'll just show you the introduction to the project, why we're doing these suites, what are the drivers for it, and then we'll just break the presentation down into the various work packages. So this was customer requirements, what do the customers want out of it, and what functions does the technology give us. And then as part of the theme for the discovery phase round 2, we did a literature review and went out to suppliers and supplier base in Europe and America. So that'll be our partner presenting on that from Newcastle University. And then we also developed some detailed design specifications and ratings for each technology that's going to be used on the LV network. So our partner at Integrated Power Tech, which is a spin-off company of Cardiff University, will take us through that detail. And then work package 4 is roadmap to commercialization, which is very similar to the structure of Alpha that we've developed as part of the project. So I'll introduce you to that and run you through the detail, and then we'll go into Q&A. So next slide, please. And again. Thank you. Okay, so drivers really mainly are about the government trying to roll out electrified heaters as quickly as possible, and also electrified transport. And the two drivers we've seen recently in announcements are 600,000 heat pumps, towards the end of this decade, and the ban of electric vehicles towards the end of the decade too. And then, as people mentioned on their presentations, the net zero target. So in the UK, we typically have single phase connections to properties, and these are thought to be reasonably well distributed across the phases, but there is masking of exactly which customer is connected to what phase, and whether there's any phase imbalance, which will drive issues later on. And these issues will become apparent when we increase penetration levels of heat pumps, EV chargers at domestic level will be 3.5 and 7 kilowatts, and things like photovoltaic panels. I doubt we'll see wind, but it's mainly photovoltaics. So when we do increase penetration levels of things like PV, we see voltage rise issues and difficulty maintaining within statutory limits towards the end of the feeders, especially on radial circuits. And we also see on interconnected networks, we can see load sharing unevenly between secondary substations, which can lead to low impedance paths getting on the load, and then those transformers being near their limits, while other transformers aren't, they're underutilized. And then as we put heat pumps and big loads onto the network that are continually operating, they're not variable, they're operating throughout the day, we could see large phase imbalances, which will increase the utilization of one phase, where it could leave the other phases, the other LV phases, fairly unutilized. So we've seen 2 of these technologies rolled out previously on trial innovation projects, which brought the TRL up to its present levels. And those were the DST, which is a smart distribution transformer, and also a DSOP, which is a distribution soft open point. And they can do similar things to a certain extent, but the smart distribution transformer is mainly enhancing the functionality of a normal transformer and sticking the functionality of power electronic devices at either end on the LV and the HV side. Whereas a soft open point does the similar thing without the transformer present, but it does that at the end of the feeders and in between 2 different networks, and transfers power across 2 networks where it couldn't do normally. So this could improve load sharing across transformers, as I mentioned before. And then the top one here has never been done in the UK level, which is an LV StatCom. And LV SATCOMs are mainly used to control power factor and reactive power. And they can do that very fast, and they can provide rapid response. And they can also improve phase and balance. So they're connected to 3 phases, and they can power share between the phases. And if they're placed optimally, they can improve the phase and balance issue where they're placed. So these are very promising technologies. And we'll just roll out into what we've done for work package 1. Next slide, please. And again. Okay, so what we did here was we looked at our network as it stands today, because we developed a modeling tool called Navi, which is kind of inspired by ENW's project, which was LV Solutions, and that used it changed a GIS model into a connectivity model, which you could derive network models from for power flow studies. So we've taken that idea ourselves and made a tool out of it for our LV design engineers and LV planning engineers. And that means that they can interface with a map anywhere across our license area, and then click anywhere on the network, and it will connect all parts of that circuit up to its nearest substation. And then you can download that program and all of the asset data within that program. And then you can superimpose different LCTs on top of it. And it's mainly a steady state model at the moment, which is adding LCT levels based on where you are in time, based on our distribution for generic energy scenarios. So the bottom picture here, you can see that the heat pump level is starting off slow, but it's accelerating towards 2040. And then the top part of the graph is showing the EV penetration levels increasing dramatically. And on the right, then we took those snapshots in Navi and showed that our networks are getting more heavily utilized on a thermal basis because it's carrying more current to customers. And at some point during that period, there will have to be an intervention on some networks that we analysed. Quite a high proportion of them that we picked. It's only a small sample, but we think that's indicative. So it's just showing that this work package is showing that there is a use case for these suite technologies, and we need to be thinking about how to do that as fast as possible. So anyway, I'll roll on to work package 2 then. If you just go on to the next slide, please. And again, and this was done by Newcastle University. So I shall hand over to the lead, which is Matt Deakin, Dr. Matt Deakin.
Okay, thank you. Yeah, so in work package 2, we were looking at a literature review and engagement with potential suppliers for these technologies. So power electronics are sort of everywhere now in the power system at all levels. But this is sort of, as Andrew mentioned, this sort of new LD suite is a sort of new potential application for power electronics. And there's these 3 aspects that the project is interested in that make it a bit unique as compared to sort of power electronic projects more generally. So we're looking at low voltage distribution. We're interested in grid connected systems rather than microgrids. You find lots of research about microgrids and power electronics. And also we're just focusing on conventional AC rather than sort of mixed AC or DC distribution. And so because there's been so much innovation in this space, we wanted to do a sort of deep dive in this discovery phase, and there's sort of 3 aspects of that. So firstly, we had a holistic review of both historic and ongoing power electronics projects so that we could look at the different types of innovations that people are doing. So for example, you can see on this figure here, there were 6 innovations that we identified from those projects, of which 3 were included within the D-Suite sort of innovation proposal going forward. We then wanted to look at the challenges that these devices have, sort of the challenges to widespread rollout, and then also talk to potential suppliers for that alpha and beta phase going forward. Next slide, please. So the project review that we undertook, so we had a sort of 3-pronged approach. So we looked at the Smarter Networks portal, which obviously has huge amounts of information on there for UK-based projects. For European projects, we used the Cordis database, and for the US, we looked at the ARPA-E project database. We surveyed 54 projects, and across those projects, we identified that there are 9 challenges that are sort of common to all of those in terms of the barriers that power electronics face for providing capacity within the D suite. So cost, reliability, these are all sort of things that might be familiar to colleagues. And the innovation types, we found that there were 6 sort of technology classes that were relevant. And having identified those, we spent quite a bit of time reviewing literature, seeing how those different innovation classes can impact on those challenges. So this figure at the bottom that you see here, this is, we've evaluated how effective different types of innovation are against those challenges. And you can see it's quite patchy, actually. So you really, if you want to sort of move forward across the board, you really need to be starting to combine those technology classes within a project. So we think that that approach that D Suite is taking is the most effective one. So as well as that, so in terms of the sort of work package output, so there's that matrix that I've just described. The project database is also given in the report, where we outline the sort of different challenges and technologies that each are looking at. And then, as I mentioned, we identified 18 suppliers that could each develop at least one of the D Suite technologies that Andrew outlined earlier. Next slide, please. Okay. I'll pass back over to Andrew.
Yep. Thanks, Matt. That's good. Yeah. So, Wenlong, would you like to present your hard work on the discovery stage for package 3?
Yeah. Thank you, Andrew. I'll take over from. Yeah. So, following on the literature review, so what we are doing, what we did in the work package 3 is to specify the design parameters for the hardware and the control algorithm for these D Suite technologies. So as Andrew mentioned earlier, so we're focusing on 4 types of D Suite devices, which are D STATCOM, D SOP, D Smart Transformer, and D HF, which is D Harmonic Filter. So we have done 3 things. So one is to develop the hardware solution, which means mainly about the topology. So we develop different type of topologies for these different devices. But what we also did is to develop a modular structure for this device, which means that they'll share the same architecture for the basic unit. Then if you want to construct a different type of these devices, then you just need to pick up more modules and then put them together, connect them together, and then you have different type of DCU devices. So that is mainly for the consideration of the cost. The other thing we have done is to do the hardware design on that module, to design the parameters, for example, what kind of switches we're using, capacitors, inductors, how to optimize them, and how to protect them under the grid fault. And we also consider the internal fault or voltage over current. So the last thing, but not least, we have done is once we got that hardware, then we developed some control method. Again, it's modular, have different layers from the bottommost switch layer control and up to the system layer control and interaction with the system. So can you go next slide, please? Right. So in terms of the a bit more details, what I mentioned the previous slides. So for the topology design, as I mentioned, we identify a 3-phase 4-wire structure as a most basic module for the DCU devices. And then, for example, for the DSOP, then essentially we just need 2 of them connected back to back. Then we have the DSOP, the software component. And for the smart transformer, so again, we need them back to back, but one of the converters can be connected in series with the transformer, with the help of auxiliary transformer, which is partially RT1. And last example I gave in the middle is the can be a D harmonic filter. So you just need one the module, which is a 3-phase 4-1 converter. Then you can inject or absorb different type of harmonic into the grid. It can be used as DSTACOM as well. Basically, they share the same hardware. So the difference is about the control, comes from the control. And the most right side, you see what I mentioned, different layers from the hardware control, switching, converter applications up to the system level control. So we designed the general structure of this control strategy and topology in the discovery phase. So going to the next phase, we're going to investigate more details. Like, for example, we have the module. So how can we optimize that module in terms of the cost efficiency, the power density, and we investigated the size, the investigate control as well. But we need to do more investigation on the protection side, especially under the grid fault. Can you go to the next slide?
Sorry, are you able to start to conclude your presentation, please, as we are coming to the end of the session?
Yeah, I think this is a summary for the work package 3. So I think I mentioned the majority of the point, but one thing I want to highlight is so the DCO devices, we got 4, but there might be more depending on the functionality needed. But what I want to highlight is they share the same modular structure. So basically you connect them in series, in parallel, so they can provide different functionalities as what is needed from the grid side. Andrew, hand over back to you.
Yes, well, I can terminate here, or I can just do very quickly 1 minute on the route to market and close. Up to you.
Sure, that sounds great. Just a quick summary would be fab.
Yeah, next slide, please. Yep, so route to market then, we structured this according to the alpha if we were successful. So the idea is work package 1 is to understand the value streams better by doing detailed network modeling on very accurate networks in minute by minute or half hourly by half hourly over the year, and then test those control philosophies and release the technical benefits for the business case. The second part of that is to nail down the hardware in terms of modularity, and then create a detailed technical specification for tender. And then this would then go into the business case standards review output for the project and work package 3. And then work package 4 then, it takes work package 2 outputs to develop the PQQ pack, which will be like a very early draft of a technical specification. Send it out to the market and suppliers we've identified in this discovery stage, get costs and comments back to see what's missing from our tender pack, and then update that tender pack for final version ready for a beta stage if we're successful. And then while we're doing all that work from work package 1 to work package 4, we'll also be going out to various sites we've identified in this discovery phase to see if they're eligible for D-Suite installation. And any of those that weren't eligible, we have contingency to select new ones and then appraise them and have them ready for selected sites by the end of the alpha stage, ready for beta. Okay, thank you very much for listening. I'll hand over to Q&A. Thank you.
Thank you so much, D-Suite. I really appreciate that presentation. We have time for one quick question from Rob Walden, which is about the communications between the devices and the cloud-hosted services for correct operation. He says, what consideration has been given to the failure modes and reversionary modes of the operation when communication is interrupted?
That would have to be done in the alpha stage. So we have experience on LV Engine and Angle DC for maloperation of the control system, which we're bringing into this project. But you need to do the detailed control studies first to understand where your monitoring points are going to be, what visibility you have of the network, and how that affects the behavior of your equipment, and is that operating within a safe operational envelope all the time. And if you lose comms or connection to your central system, what will your actively controlled device do in that scenario? And you have to have default settings which these things reduce back to. And if they reduce back to a certain extent, will that affect your benefits the benefits that are released to allow more customers to connect to PV, for example. Could we run, say, a DStatCom in a reduced operating mode and still have the required penetration levels of PV that have been released, or do we have to think of something else? So these are questions that we'll have to answer in the alpha stage, because it's very detailed modeling that needs to be done.